Okay, so for the last session of today, I guess we'll leave a bit early, but we have Esteban from Argonne. He will present HACC for Exascale Cosmology on Aurora using SYCL.
Great, thank you. My name is Esteban and I'm from Argonne National Laboratory, one of the developers for HACC, which is a cosmology code. I'm first just going to talk about sort of our experience porting HACC to SYCL, how we used cyclomatic. We did some abstraction for host site code while maintaining SYCL and CUDA. We did some performance portability comparison with HIC, CUDA, and SYCL on different GPU architectures, so the AMD, NVIDIA, and Intel GPUs. I'll talk a little bit about the performance optimizations that we did for the PVC architecture, so the data center max, preliminary results from Aurora, and some ongoing work that we're doing using developing an EDSL, so in a domain-specific language, and we're trying to ease maintaining CUDA and SYCL. So what is HACC? HACC is a cosmology code. It stands for the Hardware Hybrid Accelerated Cosmology Code. A new version of HACC uses conservative reproducing kernels for smooth particle hydrodynamics. So this is an SPH formalism that is being added to the gravity solver. This version of HACC is we call CRK HACC. It resolves some discrepancies with grid-based hydrodynamics solvers. It implements subgrid models for radiative cooling, star formation, AGNs, and such. And HACC is used to study for large scale structure formation, so the cosmological simulation code. So we started off, probably like many codes, with a CUDA source file. So on the left, you see our initial migration pipeline. Started off with CUDA, used cyclomatic, and here I should say the way that we were using cyclomatic was on an individual source file. So individual CUDA source file, we'd run through cyclomatic, we'd get SYCL device functions. We developed a simple Clang tool, so this is using Clang's lib tooling, just to convert the device function into its functor form, right? So as a device function object or as a function object. So just creating the class or struct, private members, yanking out the body, and putting that into the call operator that can be used for calling SYCL functions. And on the right, sort of a picture of the way our code looked. So down here is we had program model API wrappers for calling HIP or CUDA and SYCL. And this is what would invoke our kernels. Also, we would wrap sort of any device specific, like doing device memory allocation, memory transfers between host device, all these things. So the effort here is then to have a common host site code for CUDA and HIP or CUDA, HIP, and SYCL that doesn't change. And so all of our effort was really in porting the kernels themselves. So sort of why did we go with the function object representation? It's really this. So we have these different kernel launch forms. So in CUDA we have the triple chevron sort of syntax for launching kernels, and then for SYCL there's a couple different sort of options. Supplying a lambda function inside the parallel for region, or supplying the function object to the parallel for. And like I said, we ended up opting for using the function object form. The reason being that if we wanted to write sort of a launching sort of function or launching mechanism for kernels that could sort of be abstract, the SYCL 2020 standard doesn't allow function pointers. So without the use of function pointers, being able to call a function or being able to have a kernel launcher that could take sort of an arbitrary function and launch it became more difficult. But in C++, we can have templates that take class as a function parameter, and indeed that's what we ended up using as the wrapper mechanism for launching kernels. We did some testing. We set up some experiments to be able to compare the SYCL performance on different architectures against the native version of those same kernels. So looking at SYCL running on AMD hardware and NVIDIA hardware compared to the native HIP and CUDA versions. And we used Polaris and Frontier to do those experiments. And we'll also compare some results running on Aurora on the Intel GPUs. So the simulation was a cosmological simulation. It was 512 cube particles, 5 time steps. These were intended to be one node comparison. So the code uses a minimum of 8 MPI ranks, and our configuration was either 1 MPI rank per stack or tile for the Intel GPU. And on Polaris, since there's 4 GPUs, we used 2 ranks per GPU. On Frontier, a similar mapping to Aurora, where we had 1 rank per GCD. Sort of GCD is similar concept as a tile. And when we did this, our comparison, first we could look at Frontier. We see that the HIP version, the native HIP version, and our SYCL compiled with the AMD backend perform almost exactly the same. So near parity in performance. I should note that on different compilers like MVCC and HIPCC, the fast math option was not enabled by default. So that's why you see in the leftmost result here on Frontier that what we call HIP default was significantly larger in time. So here, lower is better on this graph. On Polaris, sort of the same thing, and also the culprit was the fast math option. But once that was enabled, SYCL and CUDA achieved near parity in performance as well. And on Aurora, there was some work to do, right? So the first thing that we did is we saw SYCL on Aurora actually perform, the performance wasn't as good as we hoped, and led to some performance optimization that I'll cover in the next couple of slides. The result of that final optimization was a significant reduction in the time on the Intel GPU. And again, here lower is better. So the optimizations that we did, were first to identify the hotspot kernels. So here, five of the most time consuming kernels, so the most compute intensive kernels. Is a brief description here for each one of these. The thing to take away is that each one of these kernels implements what we call a half-warp algorithm. So conceptually, in the simulation, we need to interact particles with other particles. And in a kind of recursive volume decomposition, we have a tree data structure with sort of like a fat leaf collection of particles. And we identify which leaves are spatially close enough to each other that all of the particles in one leaf need to interact with another set of particles in another leaf. So the way this maps down to hardware is for the SIMD layout, we pack half of the SIMD lanes with particles from one leaf and half of SIMD lanes with particles from another leaf. And then the interactions happen between the particles that are being in the different SIMD lanes. So one thing to note about the particular communication pattern and because of the equations that are involved is that there's a pairwise symmetry. So when some particle from one lane interacts with a particle in another lane, then the symmetric calculation needs to happen. And there are some data dependencies between those two different lanes. The data is being calculated those two different lanes, that it's efficient to share between them. So the kind of pattern that emerges from this is a kind of XOR based pattern, and that maps in CUDA to using the shuffle intrinsic and the matching sort of object or the function in SYCL is select from group. I know there is an XOR shuffle intrinsic, and there also is an XOR shuffle subgroup function in SYCL, and they all achieve roughly the same performance. So what was the bottleneck, I guess, right? Is so looking at the assembly produced by the shuffle intrinsic, or using select from group, you can see here that it just natively the way we used it, using the half-warp algorithm and using the select from group function, the code generated uses this indirect register access. So this is assembly dump from the Intel Graphics IGC, the Intel Graphics compiler. And the thing to note here is that the use of A registers, right? So when the compiler needs to do a shuffle pattern that it can't easily generate generate the lane exchange, you'll generate code that looks like this using these A registers, and so this kind of indirect register access is notoriously slow. More performant generation of the assembly would look something like what's on the bottom, and this is uses register regioning. So using register regioning, the compiler can generate more efficient code because it doesn't have to do this kind of indirect register access. But this sometimes is not easy to structure your code to generate something more efficient like this. So one of the things that we did was investigate the use of broadcasts. So this code at the bottom shows register regioning to generate a broad. So essentially, what you're seeing here in this last line is a broadcast, and what's happening is that the Intel instruction set is a true vector instruction set where the operands can be scalars and vectors, and what you're seeing here in blue is basically the register regioning syntax for isolating an individual SIMD lane, so a scalar quantity. So getting code to generate something like this, or being able to use broadcasts, we were able to do that, but it was having to do a significant restructuring of the loops, basically not doing that half-warp algorithm that I just described, but something sort of more analogous to what you would call, like, I guess, a full warp algorithm, where all of the particles from one leaf are read in by the entire subgroup, and they would have to read in the entire next leaf. That has a lot of register spilling. One of the reasons that we didn't try that when this was first being developed in CUDA. But on the Intel GPU, because for various reasons, you can increase the amount of registers available by changing the SIMD size or reducing the SIMD size, or even using a large register file, then it turns out for us the broadcasts were somewhat performant. Another thing, another mitigation strategy that we used, though, was just using shared local memory. And I think in the Amber code, you guys did exactly the same thing. You ran into this exact same issue where using the shuffles, it turned out to be more of a performance bottleneck. So simply just using shared local memory is a good workaround. The other thing we did too was investigate using inline assembly. So I don't cover it here in this talk, but we do have a small set of instructions, four move instructions that we can write using inline VISA, and that performance is actually pretty good. So here on this plot, here's a comparison of all of those different variants of shuffle implemented, and on using all of those 5 kernels that I just described as being the hotspot kernels. And you can see that the broadcast version is actually, very performant, but so is the inline BISA version. There's a couple kernels where it's not as performant, and it's just extras and corrections kernels. One of the reasons that you're seeing the broadcast version being the most performant there is that because of the loops being restructured the way they were, we could also reduce the number of atomic instructions that we needed to use, and that accounts for that performance difference. We do have the same plot available on in a paper we published at P2HPC that shows the same effect on the NVIDIA and AMD architectures. Now I just want to show some weak scaling that we've run on Aurora. So this was up to 1792 nodes. So HACC is designed to weak scale. So in production, we tune the problem size per node, and then the code weak scales very well. And the reason is because weak scaling is just really dependent on our FFT implementation, which we've spent quite a lot of time optimizing. So what we're seeing here is we have a figure of merit with just the number of steps times the number of sub-steps and a number of particles, which is kind of just basically like a number of particle throughput per second. And we're showing a relative FOM, right? A relative figure of merit improvement to demonstrate scaling. And we achieve quite nice scaling. Just a disclaimer, this is a pre-production state of Aurora. So and this is two studies, so two problem configurations that are very similar but still somewhat different. That's why we have a disconnection in that scaling plan. This is the same basically the same runs, but now this is the whole node. So what I was showing in this previous slide was just the GPU time. Now in the full node, so this is the entire time, everything taken on the host. There's a little bit of a weird dip here. We didn't really investigate that too much, but like I said, this is a very pre-production state of Aurora. So yeah, something could have been happening at that time. So last thing I want to talk about is we are maintaining two codes. So we have a CUDA version and a HIP version. We do have this sort of semi-automated pipeline for migrating from CUDA to HIP, but nonetheless, it's still somewhat painful, to migrate code and do testing and verification and all of that. And just sort of the code is under very active development. So just since supercomputing last year, I did a query on the GitHub on our Git repository, and we've seen 377 files get changed. 92,000 lines of code have been inserted, 3,000 deleted, 77 commits. So it's very difficult to keep track, of so many changes. So a goal. So since we were somewhat successful wrapping all of the host side code with like I said, the kernel launching mechanisms, all of these things, we figured, could we do the same thing for kernels? So our goal here was, could we design an embedded domain specific language, so something just completely written in C++ that can support all of the programming models that we want. Right now, that's just CUDA and SYCL, and have a single source, of all of our kernels. So first we have to define all of the host side abstractions, so memory management, all the memory allocations, data transfers. We need to define all of the kernel functionality that we need, so the warp or subgroup functions, group functions, all those special math functions, everything that might be native, and then define the syntax for the EDSL, and then just write all of the wrappers. And so the hope here is that this picture where we have independent CUDA kernels and SYCL kernels get turned into something that's, like I said, is written once, right? So we have EDSL kernels that basically have every sort of specific API call is being wrapped in some kind of C++ wrapper for HIP and CUDA and SYCL. So what does that look like? Well, like I said, we have we figured the function object form of our kernels. We had a way of doing that. So the natural thing for us was, can we use a function object form for CUDA? And indeed, this is what I'm showing here is that so in this bottom square as an example of what it would look like on the host using our C++ wrappers. Um, so we have something looks like this. So we embed in our namespace HACC this kernel launch. We instantiate the kernel that we want with the parameters that we want. Some of these arguments for these kernels are pointers to device functions that have already been set up using again the wrappers for the appropriate API, and then the kernel launch parameters. So this would it's analogous to the total amount of threads that we want to launch, the block size, and if there's shared memory and a stream or a queue associated with it. And right, and so this is pretty much what this looks like. The launch takes in the kernel itself, and the kernel is, like I said, an instantiated object. We call this CUDA global function that takes the kernel as a parameter. Similar to what SYCL does, we have an item that is also responsible for a lot of the indexing, or resolving what a lot of the indexing is in the parallel, like in the ND range. And then the kernel is launched using its operator and then taking the item. So this looks, it's CUDA, but it looks kind of like the way SYCL does the launch. And what does our kernel look like? So our kernel, or now our EDSL kernel, looks sort of, just like we have a few headers that include some of the functionality that we need, and then sort of almost what just like the SYCL kernel would look like, just by using the device operator. And one thing to note here is that what we experienced was we use explicit template instantiation here to have this kernel launch being sort of embedded into the compilation unit of this source file. And this was kind of important because this allowed us to avoid building CUDA's relocatable device code. And there's actually, in some of our experiments, we saw a sort of non-negligible overhead in doing this, or avoiding relocatable device code. So how good was sort of how much overhead if any, ideally with C++, there's zero cost abstraction using templates and inline functions. So how close could we get to that? And indeed, for CUDA and the basically EDSL version with the CUDA backend, we see a very small performance difference, and with SYCL, almost exact parity. And we've tested this on 2 systems available at Argonne in the JLC testing area, where we have access to an NVIDIA V100 that's for these CUDA tests were done, and then on Sunspot, which is the Intel Data Center Max. So yeah, quite good so far, and this was a simple gravity only simulation, so there's really only 2 very easy kernels to test with. We're testing this out on the more complex hydrodynamics kernels, and so far the preliminary results are pretty good. So yeah, in conclusion, we described porting HACC from CUDA to SYCL using Cyclomatic and some Clang tooling. We saw that shuffle operations were performance portable on the Intel GPU, We provided some sort of straightforward, just using shuffles or even some optimized inline VISA that can recover some of that performance loss. We showed some pre-production Aurora scaling on up to 1792 nodes. And and our ongoing work with EDSL seems to be pretty promising for supporting both CUDA and SYCL side by side. So the standard disclaimers and acknowledgements. Happy to take questions.
So Steve, why make your own EDSL instead of trying to use SYCL as your portability layer?
So we showed, excellent question, right? I mean, so we showed SYCL's performance portable and near parity on a lot of systems. I think like everybody else, right? Convincing all your developers to go with a programming model that is newer or maybe that people are less comfortable with is also, challenging, and is probably the main answer. And the other is that this EDSL sort of idea, or just wrappers and abstractions, seems more complicated than it is. I mean, I think the subset of functionality that we have to wrap across HIP and SYCL are pretty pretty similar. So right now, at least, it doesn't seem like a lot of overhead for us to maintain, but
not a question, but kind of a follow-up. Like, I feel like that might give you a sense of entitlement if you have CUDA and then you're running SYCL on the same backend. Can I get more optimization out of SYCL, right? If you have that equivalent. Just a thought.
You mean like would this or more performance?
Just say, yeah, if you have the CUDA equivalent, you can run that and see, is a SYCL kernel giving you the same performance? In a lot of cases, you don't have that CUDA equivalent.
Sure. Yeah. I mean, right now, at least it's nice to be able to run side-by-side comparisons. The other thing too about EDSL, I guess, or this sort of, wrapper sort of idea is that we have different tool chains available to us, right? Like, I mean, I can build, with like when I say I'm running this EDSL version with a CUDA backend, I'm using like the CUDA tool chain, right? Like I'm using native CUDA, I'm using MVCC. And same thing when I'm running SYCL, I'm using SYCL backend. I could even run the EDSL version of SYCL backend on NVIDIA architecture too, right? And compare that, right? So there's this crazy matrix of different ways you can build in.
That's where I was going.
Yeah.
That's a nice thing to have, I think.
Sure.
So I noticed you're using the dynamic shared memory kernel invocation in the CUDA code. Are you emulating this functionality in the EDSL on the SYCL side?
So in our CUDA kernels, we used to use, or in our production builds, we have static shared local memory that we use. Dynamic shared memory is what seemed to map more to the way SYCL does shared memory using the local accessor.
Right.
So that's why it was
That's why it's like that.
We,
Okay,
we
good.
didn't see a performance difference from using static versus dynamic.
Yeah, I thought that might be the case. All right.
Yeah.
Thank you.
The other thing too that we haven't investigated yet is that perhaps a different backend, maybe with some CPU, is also possible, right? So it's kind of you can write some kind of your kernel in sort of a way that's kind of almost independent of like I said, different tool chains and programming models even.